Welcome! Short version of the video addressing complex multiplication in polar form. If you have a complex number in polar form, using Euler's famous identity, you can rewrite this clumsy term as simply e to the power of phi I, this being the complex exponential function. And using this form, this complex number transforms into 2, which is the absolute value, the length of the arrow times e to the pi over 4i, because the angle of this arrow here is 45 degrees. Now, if we use this fact about the complex exponential function without proof, that e to the z times e to the w is the same as e to the z plus w for any complex numbers, z and w, then it becomes apparent what complex multiplication really does geometrically. Because if we take two complex numbers, z and w, write them in polar form, multiply them, and then use this equation here, it becomes apparent that the length of the arrows gets multiplied to give the length of the product arrow, and the angles or arguments simply get added. Phi plus theta is the angle of this arrow belonging to z times w. To multiply complex numbers, you simply have to multiply the absolute values and add the angles, and that's it. Using this rule, you can easily check for yourself that the product, for example, of these two complex numbers gives you 4 times e to the pi over 2i. Here I subtracted 2 pi to arrive at the unique polar form, angles between 0 and 2 pi. And e to the pi over 2 times I is nothing but the imaginary unit itself, because it has length 1 and an angle of pi over 2 or 90 degrees. Next, we take a look at this map. Write multiplication by the imaginary unit I. If I take any complex number in polar form, r times e to the phi I, and multiply it with I, which, as explained above, has this polar form, e to the pi over 2 times I, then I add pi over 2 to the angle, and r remains unchanged. So, multiplying by I simply rotates the arrow counterclockwise by 90 degrees or pi over 2 radians, and the length is unaltered. And this is, for example, very useful in electrical engineering when dealing with alternating current circuits. And as a final example, whenever you need to calculate any power of a complex number, the polar form is very useful, because if you remember, we did this in an older video. Doing this in Cartesian form, you need a trick to arrive at the result without too much work. But if I transform this in polar form, which is simply square root of 2 by Pythagorean's theorem, is this the length of this arrow, and the angle, of course, is 45 degrees or pi over 4, then I simply have to raise this to the 10th power, and this is easy because square root of 2 to the 10th power is 2 to the 5, so 32. And this here is e to the 10 times pi over 4i, which is e to the 5 pi over 2i. And this is the same as here. This is I itself, so the result is 32i. I hope that was helpful. Thanks for watching. Bye-bye.